Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Sciences, SOS, MSc. Chemistry, MSCCHEM. Semester I, MCH 011 Inorganic Chemistry I. Block 1 Main Group Elements, Transition Elements, Structure of Molecules. Unit 1 General Characteristics of Main Group Elements and Transition Elements, 1.1 Introduction. This is the first unit in the first block of the Inorganic Chemistry I course of the M.Sc. in Chemistry program. In the previous courses you must have studied that the properties of elements are a periodic function of their atomic numbers. As a result of their similar valence shell electronic configuration, elements belonging to the same group of periodic table exhibit similarities in properties. Further, they also exhibit a gradation in properties with their position in the group because of the valence electrons occupying different electronic levels. The differences in the properties of the elements arise due to differences in the atomic properties like the atomic size, ionization energy, electronegativity, etc. These atomic properties are directly related to the total electronic configurations of the elements and form an important link between the properties of elements and their electronic configuration. In this unit you will study the periodicity in these atomic properties of the main group elements in general as well as those of the transition elements. You will also be learning about Latimer diagrams. In the next unit you will be learning about the structure of molecules. Expected learning outcomes. After studying this unit you should be able to discuss the periodic trends of main group elements, configuration of multi-electron atoms. The atomic properties of the elements depend on their electronic configuration. The electronic configuration of group 1 elements are given in Table 1.1. Table 1.1, Properties of the group 1 metals. Look at the screen. The electronic configuration of group 2 elements are given in Table 1.2. The alkaline earth metals are quite soft metals, but are harder than the corresponding group 1 elements. This is because of their two valence electrons which participate in metallic bonding. Table 1.2, Properties of the group 2 metals. Look at the screen. The two terms D block metal and transition metal are often used interchangeably. However, they do not mean the same thing. Transition elements have properties which are transitional between the S and P blocks. In the S and P blocks, electrons are added to the outer shell of the atoms. The IUPAC definition of a transition element is an element that has an incomplete d subshell in either the neutral atom or its icons. The latest periodic table by the International Union of Pure and Applied Chemistry, IUPAC, periodic table of the elements, is given below in Fig. 1.1. Look at the screen. Fig. 1.1, IUPAC periodic table of the elements. The F block consists of elements in which 4f and 5f orbitals are progressively filled. They are placed in a separate panel at the bottom of the periodic table. The names inner transition metals is often used to refer to the elements of F block's elements. The D block of the periodic table contains the elements of the groups 3 to 12 in which the d orbitals are progressively filled in each of the 4 long periods. Using the IUPAC definition of transition elements, the elements of group 12 would not be called transition elements as they do not have incompletely filled d shells even in any of their compounds. Thus, 2 of the group 12 elements, zinc, Cd, are members of the D block but are not transition elements as they do not have any compounds with an incomplete d subshell. The situation for the third group 12 element, mercury, is different. Very recently it has been reported that mercury forms a compound in the mercury, IV, state, mercury 4 fluoride, which has the D8 electron configuration. This qualifies mercury as a transition metal. Using the IUPAC definition there are 4 series of transition elements and they are discussed below. The first series of transition elements, Sc. 21, to zinc, 30, here 3d orbitals are filled. Table 1.3, Electronic configuration of the free atoms and dispositive icons of the first transition series. Look at the screen. The second series of transition elements, Y39 to CD48, here 4d orbitals, are filled. Table 1.4, Electronic configurations of elements of the second transition series. The third series of transition elements L, 57, and then HF, 72, to Hg, 80, here 5d orbitals are filled. Table 1.5, Electronic configurations of elements of the third transition series. The fourth series of transition elements AC, 89, and then RF, 104, to CN, 112. Here 6d orbitals are filled. Table 1. 6. Electronic configurations of elements of the fourth transition series. Look at the screen. You have learnt earlier how the penetration of inner electron core influences the radial distribution functions of various orbitals. The extent of penetration decreases as S greater than P greater than D greater than F. The way in which the energy levels of different individual orbitals change in multi-electron atoms depends a lot on the population of other levels. You have studied previously that all the subshells of a principal shell, like those of 3s, 3p, 3d, of a hydrogen atom have the same energy. The same is not true for complex atoms, where the ns orbitals, which penetrates most, have the highest increase in effective nuclear charge. So, the energy of ns orbitals drops much below the corresponding energies of the np or the nd atomic orbital. In multi-electron system, the FOS orbital lies a little lower in energy than the 3d orbital. But the situation changes when the 3d orbitals get filled up with some electrons. If you follow the Fig 1.2, you will understand the radial distribution curves of the 3d and FOS orbitals. Thus, after argon, in potassium and calcium, the electrons enter the FOS orbital rather than 3d. The radial distribution functions for the two orbitals is shown in Fig 1.2. Look at the screen. Fig 1.2, radial distributions of 3d and FOS atomic orbitals in H atom, qualitatively. After the addition of a few 3d electrons, the energy of the 3d orbitals fall below the FOS level quite fast because the 3d electrons experience more effective nuclear charge. So, at the beginning you will see that the FOS orbital has lower energy. But if you look at Fig 1.2, you will see that, on addition of some electrons in 3d level, the 3d orbitals becomes lower in energy than those of FOS. Let us study the last electrons in K and Ca enter the FOS orbital after argon core. As FOS is more stable than 3d. But since the FOS and 3d orbitals are very close to each other in energy, the last electron in Sc has the 3d orbital occupied, having the ground state electron configuration as 3d. 14s. 2. But the relative ordering of the energy levels in scandium changes as the binding energy of the 3d electron rises suddenly. Thus it would require much more energy to remove the electron in 3d than that in FOS. Hence the ground state configuration of the Sc ion is a 3d 14s. 1 and not a 3d O FOS. 2. After zinc, a FOS. 23d. 10. That comes the p block elements as you can see in the periodic table in Fig 1.1. The next lowest available orbital is 4p, which has the capacity of taking up a maximum of 6 electrons. So in the next 6 elements, the 4p orbitals are filled in a regular manner. The noble gas krypton, Car, has the configuration a 3d 100 FOS. 24p. 6. Thereafter comes the question, which orbital will be filled up first, 4d or 5s and 5p? Well, the 4d orbital has higher energy compared to 5s and 5p. So, the 2s block elements come after that, followed by the second transition series, with Y as Car 4d 15s. 2. And Ag as Car 4d 105s. 1. Thereafter comes CD as Car 4d 105s. 2. And the 6p block elements, which ends at the noble gas X as a 4d 105s. 25p. 6. After this the 4f, 5d and 6 orbitals are available. Now, if you look at the Fig 1.2, where the variation of energies of atomic Orbitals are shown against the increasing atomic numbers. You can notice that around Z equals 50, the change in energy of the individual atomic orbitals is very complicated. The 4f orbital cannot penetrate much in the xenon core and so has little stability. But the situation changes when the 6 orbital gets filled up with 2 electrons, into which the 4f penetrates much. Thus the enhanced nuclear charge sharply lowers the energy of the 4f orbital. You can see in Fig. 1.2 that the lines for 5d and 4f orbitals merge in this region of atomic number. In the third transition series, which starts with L, the last electron enters a 5d orbital. Thus from lanthanum to lutetium, they are classed as lanthanoids. The electronic configurations of transition elements of 4d, 5d and 6d transition series are given in Table 1.3, Table 1.4 and Table 1.5 respectively. In the first transition series, V has the configuration A, 3d. 34s. 2. The next element is Cr, which should have another electron entering the d orbital, thus making it a 3d. 44s. 2. Whereas the actual configuration is a 3d. 54s. 1. Which is half-filled and preferred. Next let us look at the configuration of Cu of first transition series, which follows Ni, a 3d. 84s. 2. This is also a very interesting case. It should have been a 3d. 94s. 2. But instead it prefers the more stable completely filled configuration, which is a 3d. 104s. 1. So, you can see that exactly half-filled and completely filled orbitals are more stable for both the first and second transition series. This is because half-filled and completely filled orbitals have an exchange energy which is much greater than the exchange energies associated with any other configuration. Let us compare the exchange energy for two possible configurations, 3d. 44s 2 and 3d. 54s 1 for chromium. Electrons present in 4s orbital in two configurations contribute nothing to exchange energy as they do not constitute any pair with parallel spin. 4. Unpaired d electrons in first configuration can make 6 pairs of electrons with parallel spin which contribute towards exchange energy, 6 combinations. Whereas 5 unpaired d electrons in second configuration contribute more towards exchange energy because they can constitute 10 combinations of pairs of electrons with parallel spin. This gain of exchange energy, worth of 4 combinations, would favor the 3d. 54s. 1. Configuration for chromium. But, you should remember that in achieving this configuration, there would be loss of energy in promoting an electron from 4s to 3d orbital. In case of chromium, the gain in exchange energy is more than the loss in energy and therefore, 3d. 54s. 1. Is the favored configuration. After argon, the 4s orbital is filled in K and Ca while the nuclear charge increases by 2 units. As electrons start entering the 3d orbitals, the 3d electrons exert more screening on the 4p orbitals than on the remaining 3d orbitals. Hence 3d remains the lowest available orbital. 1.2.2 Periodic trends in properties. Atomic radii. Atomic radii are a measure of the size of the atoms. Atomic radii are important because other atomic properties like ionization energy, electronegativity etc. can be related to them. We have to specify the bonding conditions under which the size is being measured. Pertaining to 4 major types of bonding, atomic radii are of following 4 types. I. Covalent radius. E. Crystal or metallic radius. E. Van der Waals radius. IV. Ionic radius. Covalent radius is defined as 1/2 of the distance between the nuclei of 2 like atoms bonded together by a single covalent bond. If in a homonuclear diatomic molecule of A type, e.g., F2, Ci2, bridge 2, I2, Ra A is bond length or internuclear distance and Ra is the covalent radius of atom Ra, then Ra equals 1/2 Ra A. In a heteronuclear diatomic molecule of a B type, if the bonding is purely covalent, then the bond length Ra B is equal to the sum of covalent radii of A and B, i.e., Ra B equals Ra RB. If there is a difference in the electronegativities of the bonded atoms, the bond does not remain purely covalent, it causes shortening of the bonds. Shoemaker and Stevenson have proposed the following relationship between the shortening of the bond and the electronegativity difference of the atoms. Ra B equals Ra Rb 0.07, Za Xb. 2. Here Xa and Xb are the electronegativities of A and B, respectively, about which you will study in later in this unit. Table 1. 7. Covalent and van der Waals radii of elements. Look at the screen. Adjacent molecules is the van der Waals radius of chlorine atom, whereas half of the distance between the two nuclei X and Y in the same molecule is the covalent radius of chlorine atom. The van der Waals radii represent the distance of the closest approach of an atom to another atom it is in contact with, but not covalently bound to it. Fig. 1.3. Covalent and van der Waals radii of solid chlorine. Metallic radius is defined as 1/2 of the distance between the nuclei of two adjacent metal atoms in the close-packed crystal lattice. For example, the internuclear distance between two adjacent Na atoms in a crystal of sodium metal is 383 pm, so the metallic radius of Na metal is 382 halves, i.e., 191 pm. Ionic radius is defined as the distance between the nucleus of an ion and the point up to which the nucleus has influence on the electron cloud. All common cations are smaller than all common anions except for the rubidium and cesium cations, largest single atom cations, which are larger than oxide and fluoride anions, smallest single atom anions. This happens as not only there is a loss of electrons from a partially filled outer shell on cation formation, but there is also an increase in the overall positive charge on the ion. Conversely, in anion formation, the addition of an electron to an atom increases the size due to increase in interelectronic repulsion in the valence shell and decrease in effective nuclear charge. In general, there is a decrease in size from anions to covalent radii of corresponding atoms to cations. Thus in a series of isoelectronic species, e.g., N3, O2, Na, Na, Mg2, Ul3, the greater the effective nuclear charge, the smaller is the radius of the species. In Table 1.8, radii of some of the common icons have been listed. The alkali metals are the largest in their corresponding periods in the periodic table. The size of the atom or its ion increases on descending the group. Table 1.8. This is due to the addition of an extra shell of electrons as we move down the group from one element to the next. The addition of the extra shell of electrons outweighs the effect of increased nuclear charge and thus there is an increase in size from Li to Cs. This trend is shown in Fig. 1.5. The atoms of the alkaline earth metals are smaller than those of the corresponding group 1 elements. This is because of the increase in effective nuclear charge with the increase in atomic number. Due to increase in effective charge, valence shell electrons are pulled in more firmly by the nucleus, thereby reducing the size of the atoms. Similarly, their ionic radii are also smaller than those of group 1 elements because the removal of two orbital electrons increases the effective nuclear charge even further. Table 1.8. Metallic and ionic radii of elements. Look at the screen. The trend in the variation of the metallic radii in alkaline earth and transition metals whose values are given in Table 1.8 is shown in Fig. 1.6. You can see in Fig. 1.4 that as we move from alkali metals to alkaline earth metals and from alkaline earth metals to the transition elements, the radii decrease steeply, but within transition elements this rate of decrease is less. This could be due to an increase in interelectronic repulsion after the addition of sufficient number of electrons in the d orbitals to the gradual increase in size. Fig. 1.4. Trends in metallic radii of alkaline earth and transition metals of 4th, 5th and 6th periods. Factors affecting the atomic radii. Before describing periodicity in atomic radii, we shall first discuss two of the factors which affect them. A. Principal quantum number, n. As the principal quantum number, n, increases, the outer electrons get farther and farther away from the Nucleus and hence the atomic radius generally increases. B. Effective nuclear charge, Z. You know that the magnitude of effective nuclear charge determines the magnitude of the force of attraction exerted by the nucleus on the outermost electrons. Greater the magnitude of effective nuclear charge, greater is the force exerted by the nucleus on the outermost electrons. Hence, the electron cloud of the outermost shell is pulled inward nearer to the nucleus and consequently its distance from the nucleus, i.e., atomic radius decreases. Effective nuclear charge, Z, is the amount of positive charge felt by the outer electrons in an atom. It is always less than the actual charge, Z, of the nucleus of the atom. The effective nuclear charge felt by an outer electron depends upon the actual nuclear charge and the number and type of inner screening electrons. Thus, Z equals Zs, where S is the screening or shielding constant. You can estimate the value of screening constant, S, with the help of Slater's rules in the following manner. I. Write out the electronic configuration of the element in the following order and groupings: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6, 6p, etc. E. Electrons in any group higher in this sequence than the electron under consideration contribute nothing to S. For example, in T atom, electronic configuration: 1s, 2, 2s, 2, 2p, 6, 3s, 2, 3p, 6, 3d, 2, 4s, 2. The two electrons in 4s orbital will contribute nothing towards the screening constant for an electron in 3d orbital, E, then for an electron in an ns or np orbital, A. All other electrons in the ns, np group contribute S equals 0.35 each, except for the electron in 1s, which contributes S equals 0.30. B. All electrons in the n1 shell contribute S equals 0.85 each. C. All electrons in n2 or lower shells contribute S equals 1.00 each. IV. For an electron in an nd or nf orbital, A. All electrons in the same group, i.e., nd or nf, contribute S equals 0.35 each. B. Those in the groups lying lower in the sequence than the nd or nf group contribute S equals 1.00 each. Applying Slater's rules, we shall now calculate the Z for an electron in K and zinc atoms. I. Electronic configuration of K equals 1s, 2, 2s, 2, 2p, 6, 3s, 2, 3p, 6, 4s, 1. Grouping of orbitals will be 1s, 2, 2s, 22p, 6, 3s, 2, 3p, 6, 4s, 1. Value of screening constant for an electron in 4s orbital will be S equals 0, 83 by 8, 1 by 10, equals 16.80. Hence, the effective nuclear charge Z equals Zs equals 1916.80 equals 2.20. E. Electronic configuration of zinc equals 1s, 2, 2s, 2, 2p, 6, 3s, 2, 3p, 6, 3d, 10 4s, 2. Grouping of the orbitals gives 1s, 2, 2s, 2, 2p, 6, 3s, 2, 3p, 6, 3d, 10, 4s, 2. Value of screening constant S for an electron in 4s orbital will be S equals 0, 35 by 1, 0, 85 by 18, 1 by 10, equals 25.65. Hence, the effective nuclear charge felt by 4s electron will be Z equals Zs equals 3025. 65 equals 4.35. If we consider a 3d electron in zinc, the grouping is as above, but the effective nuclear charge felt by a 3d electron will be Z equals Zs equals 30, 9x 0.35, 18x 1.00, equals 8.85. Thus, you can see that an electron in 3d orbitals in zinc is more strongly held by the nucleus than that in 4s orbital. In Table 1.9, values of effective nuclear charge for electrons in valence Shell for the first 30 elements calculated by Slater's rules have been listed. There is a steady increase in Slater's Z across rows of the periodic table. Effective nuclear charge felt by electrons also depends on the oxidation state of an atom in a compound. The higher the oxidation state of the atom, the higher will be the effective nuclear charge felt by the electrons, and therefore, smaller will be the atomic radius. Thus, the ionic radius of Fe3 ion will be smaller than that of the Fe2 ion. Table 1.9, Effective nuclear charge for first 30 elements. Periodicity in the atomic radii. We will now consider the periodicity in the atomic radii. Two general periodic trends are found for all four types of atomic radii. These are, the atomic radii decrease along a period and generally increase down a group in the long form of the periodic table, Fig. 1.9. These changes in effective nuclear charge n, the principal quantum number in the periodic table. As shown in this table 1.9, there is a steady increase by 0.65 units in the value of Z from alkali metals to halogens for the elements of period 2 and 3. But there is no change in the value of N because the electrons fill the same principal shell. As a result of this, there is a steady decrease in the covalent radius from 123 and 156 pm for Li and Na to 64 and 99 pm for NCI, respectively. Fig. 1.5, Variation of covalent radius with atomic number. In comparison to the above, the decrease in covalent radii across a transition series is much smaller. It is already discussed that across a transition series, there is only a small increase in effective nuclear charge by 0.15 units, therefore, only a small decrease in atomic radius from one element to another takes place. Across 10 elements of the first transition series, there is an overall decrease in covalent radius by 19 pm, which is much less than that across 7 normal elements of period 2, 59 pm, and period 3, 57 pm. But, due to this, the covalent radii of elements from Ga to Car, following zinc, become much smaller than that expected by simple extrapolation of the values for elements of period 2 and 3. For example, the covalent radii of Al and Ga are equal, whereas the covalent radii of elements Ge, as, say, bridge, are only slightly larger than those of corresponding elements C, P, sand, Cl of period 3. In the lanthanoid elements, filling of N2, F orbitals takes place, while simultaneously the nuclear charge increases. The electrons in the N2, F orbitals shield the Ns electrons, which largely determine the size, from the increase in nuclear charge almost completely, S equals 1.00. As a result of this, there is only a small decrease in the atomic radius from one element to another. But there are 14 elements in the series. There is a total contraction of 13 pm across the series from L, Z equals 57, to Lu, Z equals 71. This is known as lanthanoid contraction, because of which the atoms of elements HF to Hg following Lu are unusually smaller than they would be if the lanthanoids had not been built up before them. Lanthanoid contraction almost exactly cancels out the effect of the last shell added in the sixth period, and therefore, the transition elements of 4D and 5D series have almost the same atomic radii. On descending any group of the periodic table, the number of electrons in the valence shell remains constant, but the number of shells around nucleus increases monotonically. The effective nuclear charge felt by valence electrons stays nearly the same. So, with the increase in principal quantum number, n, of the valence shell, an increase in atomic radii is generally 28. Observed down any group of the periodic table. There is an increase in the atomic radii of alkali and alkaline earth metals as we proceed downwards in the group. But as discussed earlier, with the inclusion of 3D transition elements in period 4, increase in the radii of elements from Ga to bridge is smaller than expected. Similarly, because of inclusion of lanthanoid elements in period 6, atoms of the transition elements of this period, HF to Hg, are almost of the same size as the atoms above them in period 5, Zr to Cd. After that, only a Small increase in size of the remaining elements of period 6, Ti2 at as compared to the size of elements above them in period 5, into I, is observed. Fig. 1.6 shows the variation in radius of the M2 icons for 6 coordinate complexes of the transition metals of 3D series. You should remember that the 3 of 3D orbitals, T2 grams, dxy dzx dyz, point between the ligands and the other two, e.g. 222 xyz, d, point towards the ligands. In low-spin complexes, the electrons occupy the T2g orbitals first, so the radius decreases along the series till it reaches d6. Iron, Fe2. If we consider that the effective nuclear charge increases, then the decrease in size is more than this reason only. After d6, the electron enters egg orbital and so they repel with the ligands which are pointing towards them. So, if we consider the metal-ligand distance, the effective ionic radius increases. If we look at the high-spin complexes, all the 5 3D orbitals are filled before getting paired up. So far d2, d3, the radius decreases, but when it becomes d4, the electron goes to Eg orbital and the radius increases. At d5, Mn2, the value of ionic radius gives values for which the increase in effective nuclear charge is the answer. In d6, there is pairing of electrons, first, in T2 grams, which does not repel with those of the ligands. Lastly, the electrons pair with those in Eg orbitals and so they repel with ligands. Fig. 1.6, the ionic radii of the M2 icons of the 3D metals. Where there are alternatives, red represents high-spin and blue low-spin complexes. In the orbital energy diagrams, the 3 lower levels are the d orbitals that point between ligands and the 2 upper levels are the d orbitals point directly at them. 1.2.4 Atomic volume and density. There are 2 general trends observed in the densities of the elements in the periodic table. Along a period there is a general increase in density because of the increase in atomic mass and decrease in the size of the atom. Thus, in a particular period the alkali metals have the lowest density, considering the solid element structures are often the same within any group. The factors which determine the density are atomic mass and volume. As you can see from table 1.1, density increase as we move from Li to Cs. This means that the increase in atomic weight from one element to the next in passing down the group overweights the effect of increase in the size of the atom. There are, however, some exceptions to this general trend, and in this particular group of alkali metals, you can see from table 1.1 that the density of potassium is less than that of sodium. Thus, potassium is an exception in this trend. The alkaline earth metals are denser than the group 1 metals because they have 2 valence electrons per atom for bonding the atoms into a metallic lattice, and as a result more mass can be packed into a smaller volume. The density decreases slightly on moving down the group from B to C but increase considerably thereafter up to Ra. The size of an atom of an element is related to its atomic volume. So their trends are the same. Similarly, density is also related to the size of the elements. So, across the period, the smaller the size, the higher is the density of the elements. Thus there is a general trend of increasing density across the elements of a transition series. This is well represented in Fig. 1.7, which gives the variation of the densities of alkali, alkaline earth and the transition metals of the 4th, 5th and 6th periods. For 4D and 5D elements, this increase is not that regular as the increase in densities for 3D elements. Along the group, also, the density increases. Fig. 1.7. The increase in density within the D block groups is greater than that within the S and P block groups. On descending one of the main groups of elements in the S and P blocks, the size of the atoms increases because extra shells of electrons are added. The elements in the first group in the D block, group 3, show the expected increase in size, SC Weiler. But in the subsequent groups, 4 to 12, there is an increase in radius of 0.3 to 13 pm between the first and second member, but Very little increase between the second and third elements. This trend is shown both in the covalent radii, table 1.7, and in the ionic radii, table 1.8. Between lanthanum and hafnium are the 14 lanthanoids, in which the antipenultimate shell of electrons is filled. The atomic volumes of the transition elements are low as compared with elements in neighboring groups 1 and 2. Can you say why is it so? Well, it is because the increased nuclear charge is poorly screened, and so the electrons are attracted more strongly by the nucleus. Again, the extra electrons added occupy inner orbitals. As a result, the densities of the transition metals are high and are greater than 5 GCM3. The only exceptions are Sc 3.0 GCM3 and YNT 4.5 GCM3. The densities of the second row are high and third row values are even higher. The two elements with the highest densities are osmium 22.57 GCM3 and iridium 22.61 GCM3. Fig. 1.7 Trend in densities of the alkali, alkaline earth and transition metals of 4th, 5th and 6th periods. There is a gradual decrease in the size of the 14 lanthanoids from cerium to lutetium. This is called the lanthanoid contraction, which we have already discussed. The second and third row transition elements have similar radii. As a result, they also have similar lattice energies, solvation energies and ionization energies. Thus, the differences in properties between the first row and second row elements are much greater than the differences between the second and third row elements. The effects of the lanthanoid contraction are less seen towards the right of the D block. 1.2.5 Melting and boiling points. The alkali metals are soft and can be cut with a knife. As a result of increase in size and repulsion of the non-bonded electrons, their cohesive energy and tendency for metallic bonding decrease down the group, and thus softness increases as we go down from Li and Cs. These metals have low melting and boiling points, which also reflect the low values of cohesive energy between the atoms. Their melting and boiling points decrease as we go down the group. The group 2 metals have higher melting points when compared to the group 1 metals. The reason being 2 charge on the cations in the metallic lattice, causing them to be more strongly attracted to the sea of electrons and making it difficult to pull them apart. The melting and boiling points of the transition elements are generally very high. Transition elements typically melt above 1000 degrees Celsius. There are a few exceptions. The melting points of La and Ag are just under 1000 degrees Celsius, 920 degrees Celsius and 961 degrees Celsius respectively. Other notable exceptions are zinc, 420 degrees Celsius, Cd, 321 degrees Celsius, and Hg, which is liquid at room temperature and melts at 38 degrees Celsius. The last three behave atypically because the D shell is complete, and D electrons do not participate in metallic bonding. The high melting points are in marked contrast to the low melting points for the S block metals Li, 181 degrees Celsius, and Cs, 29 degrees Celsius. As the process of boiling requires almost complete breaking of bonds, and such metallic bonding exists in the liquid state to some extent, high temperatures are necessary. Therefore, the boiling points of the metals are much higher than melting points. Fig. 1.9 Trends in melting points of alkali, alkaline earth and transition metals of 4th, 5th and 6th periods. The melting points of the transition elements depend upon the strength of the metallic bond, which increases with the availability of the electrons to participate in bonding. If you look at Fig. 1.10, then you can see that between calcium and scandium, where D electron first appears, there is a jump of nearly 700 degrees in centigrade scale in the melting point. The unpaired D electron leads to higher interatomic forces and therefore the increase in strength of the metallic bond, which is reflected in high melting and boiling points. But this cannot be generalized and there are anomalies. When we move across any period in the periodic table, the values of the melting point first increases till the middle of each transition series and then it decreases with the onset of pairing of electrons. If you look at the values of melting points, for the first transition series, Fig. 1.10, there is a sharp decrease of melting point at manganese, which has 5 unpaired d electrons. This is because of a complex crystal structure of manganese. Now, the reason for the softness and low melting point of zinc, Cd and Hg is a liquid, is that the electrons are paired up in these atoms. The melting points of the elements of the first transition series are comparatively lower than those of the elements of the second and third transition series. This trend is very well illustrated in the Fig. 1.10. The periodic trends in the boiling points are similar to those in the melting points. Ionization energy. The energy required to remove the least strongly bound electron from an isolated gaseous atom in its ground state is known as the ionization energy. You can represent this process by the following equation. M.G.M. G.A. Since more than one electron may be removed from an atom, the energy required for the above is called the first ionization energy. Second ionization energy is the energy required to remove an electron from a univalent cation. That is, to cause the following reaction to occur. M.G.M. 2 grams A. The ionization energy, I, of an outer valence electron is related to the effective nuclear charge felt by the electron and its average distance from the nucleus. As given below. 1 Av. 2 Z. A. 2 IR, where Z is the effective nuclear charge, A is the charge on electron and 1 Lr. Av is the average value of I, R being the distance of the electron from the nucleus. Thus, the higher is the effective nuclear charge felt by the electron, the higher will be the ionization energy. Also, the farther the electron is from the nucleus, the lower will be the ionization energy and vice versa. Also, completely filled and half-filled subshells are comparatively more stable, because removal of an electron from them requires more energy. The valence shell electronic configurations of noble gases are exceptionally stable and, therefore, their ionization energies are the highest in the respective periods. Try the following SAQ to see whether you understand the effect of various factors on ionization energy. Periodicity in ionization energy across periods. Now, we shall examine the variation in ionization energy across the periods and down the groups in the periodic table. Values of ionization energies of elements are given in Table 1.10. Table 1.10, ionization energies of elements in KJ-MO1. However, the variation of ionization energy in a particular group or period is best shown by plotting ionization energies against atomic number. Group 1 elements acquire the electronic configuration of the preceding noble gas elements. Thereby they have a high tendency of giving up the single outermost electron to form univalent cations. Their first ionization energies are the lowest in the respective periods and so, they are the most reactive of all the metals. As we go down the group, their atomic size increases, their ionization energies decrease, resulting in an increase in their reactivity. The effective nuclear charge felt by the electrons increases after the removal of one electron from the atom of any element and hence, their second ionization energies are always higher than the first. However, in the case of alkali metals, the uni-positively charged ions, Li, Na, K, etc., have the stable electronic configuration of the preceding noble gases. Removal of an electron from a stable noble gas configuration is extremely difficult. These metals, therefore, form univalent cations only. So you see, these elements have high electropositive or metallic character, which increases as we move down in the group from Li to Cs. In fact, Rb and Cs are so highly electropositive that they emit electrons even when exposed to light, that is, they exhibit photoelectric effect. The first ionization energy, Table 1.10, of alkaline earth metals is more than that of corresponding alkali metals. This because the alkaline earth metals have higher effective nuclear charge and are smaller in size, thereby the electrons are more tightly held to the nucleus. The second ionization energy of these elements is almost twice their first ionization energy. This is because Once one electron has been removed, the effective nuclear charge felt by orbital electrons is increased, so that the remaining electrons are more tightly held. And hence, much more energy is needed to remove the second electron. However, their second ionization energy is less than that of the corresponding alkali metals because of stability of closed shell configuration of the univalent cations that are formed in the latter cases. The ionization energy of alkaline earth metals also decreases on moving down the group. Lower second ionization energies of the alkaline earth metals as compared to those of alkali metals can be exemplified as below. Fig. 1.10 shows the plot of first ionization energies of the elements of first 6 periods against their atomic numbers. As is evident from the figure, the first ionization energy generally increases from alkali metals to noble gases across any row of the periodic table. But the increase is not perfectly regular. We will consider this aspect a little later. Fig. 1.10 Variation of ionization energy with atomic number. Source: Pono, CC by SA 4.0. You have already studied in that across any row of the periodic table, the effective nuclear charge steadily increases and the atomic radii decrease. These two effects reinforce each other to increase the ionization energy across a period. Thus, the ionization energies of the alkali metals are the lowest and those of the noble gases are the highest in their respective period. But as pointed out earlier, the increase is not smooth and some anomalies are observed. For example, in the elements of period 2, in spite of increase in Z and decrease in R, the first ionization energies of B and O are lower than those of B and N, respectively. However, these anomalies in the trend in ionization energy can be explained by electronic structures of these elements. In case of beryllium, the electron is removed from the filled 2 subshell, whereas in boron, the electron is removed from the singly occupied 2p subshell. The 2p subshell is higher in energy than the 2s. So, the 2p electron of boron is more easily removed than a 2s electron of beryllium. When we come to nitrogen, we find that we have a half-filled 2p subshell. Electronic configuration is 2 2s, 2, 2p, 3, dot. While in oxygen the 2p subshell is occupied by 4 electrons. The fourth electron in this 2p subshell is in an orbital already occupied by another electron. So, it experiences considerable repulsion. As a result, this electron is more easily removed than one of the electrons from a singly occupied orbital in nitrogen atom. Thus, the ionization energy of oxygen becomes less than that of nitrogen. Similar anomalies are observed in elements of period 3, where the first ionization energies of magnesium and phosphorus are higher than those of aluminium and sulfur, respectively. You have already studied in that across a transition series, the increase in effective nuclear charge and consequent decrease in atomic radius is small. Therefore, increase in their first ionization energies is also small. But following the transition elements, the first ionization energy drops abruptly in gallium, indium and thallium. This, again, is due to the removal of an electron from the singly occupied np orbitals, which are of relatively higher energy than the ns orbitals of zinc, Cd and Hg. Trends in ionization energy down the groups. You have already studied that on moving down a group of S and P block elements in the periodic table, effective nuclear charge remains almost steady. But there is a general increase in the atomic radius due to increase in the value of the principal quantum number, n. Thus, the dominant factor in determining the ionization energies of the elements on moving down the groups is their atomic radius rather than the effective nuclear charge. Therefore, as expected, the first ionization energies decrease down the groups in case of the main group elements in the periodic table. But in the case of transition elements, opposite trends are observed. Thus, the first ionization energies of the corresponding elements of 3D and 4D series are almost similar. But these are smaller than the first ionization energies of the elements of 5D series. Certainly, the higher values of ionization energies of the 5D transition elements are consistent with the relatively smaller size of their atoms. Trends in successive ionization energies. We have already defined successive ionization energies, i.e., second, third, etc. Values of 8 successive ionization energies of first 20 elements are listed in Table 1.11. Table 1.11, Successive ionization energies, kJmo1, of first 20 elements. The tendency to form cation, i.e. metallic, character decreases across a period n, increases down the group. For example, in period 3 metallic character decreases from Na to Cl, whereas in the elements of group 14, C is a non-metal. C and Ge are semi-metals or metalloids, whereas Sn and Pb are metals. It is evident from the values in the table 1.11 that the successive ionization energies of an element inevitably become larger because the removal of successive electrons leaves a higher charge on the nucleus to hold the remaining electrons. It is also clear from the table 1.11 that the difference between successive ionization energies of the same element is not constant. Big jumps occur whenever an electron from a subshell of lower principal quantum number is removed for the first time. For example, for alkali metals, the second ionization energies are much higher than the first. For alkaline earth metals, the third ionization energies are much larger than the second, and for the halogens, the eighth ionization energies are much greater than the seventh. These cannot be explained on the basis of increase in nuclear charge alone. The stabilities of closed shell configurations similar to those of noble gases are more important in these cases. In this section so far you have studied that the ionization energy generally increases across a period and decreases down the group in the periodic table. Electronegativity. Next you will learn about electronegativity of an element, the tendency of attracting the electron pair towards itself by an atom in a molecule has been termed as electronegativity of the element. It is not a directly measurable physical quantity, but rather a theoretical concept for which several numerical scales have been developed. This concept was first developed by Pauling. He defined it on the basis of the patterns discernible in the single bond energies of elements, which were derived from the thermochemical data, where EAA and EBB are bond energies of AA and BB homonuclear bonds. As the largest electronegativity difference on the scale between the most electronegative element fluorine and the most electropositive element cesium came out to be 3.3, Pauling assigned arbitrarily a whole number value 4.04 fluorine so that values of electronegativity of all elements remain positive. In Table 1.10, the values of electronegativity of different elements are represented in boldface as calculated by Pauling using the above formula for differences in electronegativity. Mulliken defined electronegativity as the mean value of first ionization energy and first electron affinity. Both quantities are given a positive value if loss of electron involves absorption of energy and gain of electron involves release of energy. According to this relationship, a very electronegative element has a very high ionization energy, so it will be difficult to remove its electrons. It also has a very high electron affinity, hence, a very stable species results when electrons are added. The electronegativity values on Mulliken's scale are about 2.8 times those of Pauling's values. The trends in the variation of electronegativities are, however, the same. Table 1.12, Electronegativity values of elements. Look at the screen. According to Allred and Rochow, electronegativity is equated to the force of attraction between an atom and an electron separated by a distance equal to the covalent radius of the atom, where Z is the slater's effective nuclear charge, A the electronic charge and R the covalent radius, a plot of Pauling electronegativities against Z, R, 2, gives approximately straight line. Values of the slope and intercept indicate that on the Pauling scale, Allred-Rochow electronegativities are given by the numerical relationship 0.744, 3598 to R, Zx, where value of R is in pm. This method has an advantage in that it can be applied to a comparatively larger number of elements. Electronegativities of elements on Allred-Rochow scale have been listed in Table 1.12. All the electronegativity scales give average values of electronegativities of elements in different bonding environments. The larger the difference between the electronegativities of two elements, the more polar will be the bond between these elements. Periodicity in electronegativity. Electronegativity values of elements show a fairly discernible periodic trend. Throughout the periodic table, the trend is similar to that of ionization energies. Thus, as expected, electronegativity of elements increases sharply across a row of S and P block elements, since the effective nuclear charge of these elements is increasing sharply, for example, from lithium to fluorine. However, across a series of transition elements, the increase in electronegativity is much smaller. This is because the additional electron is being added to an inner shell, which provides relatively good shielding for the outer electron from the nucleus. On moving down a group of representative elements, for example, in the lithium group, there is a general decrease in electronegativity. The decrease is relatively small except between the first two elements. The much greater electronegativity of lithium row elements correlates well with their small size. As expected, the elements of period 4 from gallium onwards, i.e., Ga, Ge, as Say and bridge, have greater electronegativities than would be expected by extrapolation from values for the first two elements in the respective groups. This is due to the insertion of transition elements, because of which the effective nuclear charge of these elements is greater than that if the transition elements were not there. Similarly, the presence of the lanthanoid elements is responsible for greater electronegativities of the elements of 5D series than would be expected by extrapolation from values of the elements of 3D and 4D series. Transition elements have fairly low values of electronegativity. It increases from Sc to Cu with a fall at Mn and zinc. But this increase in electronegativity is much slower as the additional electron is being added to an inner shell, which provides relatively good shielding to the outer electrons from the nucleus. Thereby the elements become slightly less metallic, which is reflected in the increasing positive electrode potentials of their icons M2 and M3, Table 1.11. Fig. 1.11, periodic variation of electronegativity with atomic number for the first 6 rows of the periodic table. Electrode potential. When a metal is placed in a solution of its icons, a potential difference is set up between the metal and the solution. This concept is illustrated in Fig. 1.12. Look at the screen. The value of this potential difference for a particular metal depends upon the particular metal, the concentration of the metal icons in solution, and the temperature. By convention, the potential difference set up in a 1M solution of metal icons at 298 K is called the standard electrode potential. Measuring the standard electrode potentials is absolutely impossible. It has to be measured against some reference electrode, which is the hydrogen electrode. This consists of hydrogen gas at 1 atmosphere pressure in contact with a 1M solution of its icons at 298 K. The values of some standard electrode potentials for the elements of first transition series are given in Table 1.13. Electrode potential is a measure of the electropositive character and the reactivity of the metals. You will find that along a period, generally there is a decrease in electropositive character, and also the reactivity of metals also decreases. Table 1.13 contains the thermochemical parameters related to the transformation of the solid metal atoms to M2 icons in solution and their standard electrode potentials. If you look at Table 1.7, you will see that all the elements of the first transition series, except copper, have negative values and can react with acids, H, producing hydrogen. A plot of variation of the electrode potential of the transition elements of 3D series is shown in Fig. 1.16. The unique behavior of Cu, having a positive E0, accounts for its inability to liberate H2 from acids. Only oxidizing acids, nitric and hot concentrated sulfuric, react with Cu, the acids being reduced. The high energy to transform Cus to Cu2, UC, is not balanced by its hydration enthalpy. The general trend towards less negative E0 values across the series is related to the general increase in the sum of the first and second ionization enthalpies. It is interesting to note that the value of E0 for Mn, Ni and zinc are more negative than expected from the trend. Fig. 1.13 Trends in electrode potentials of transition metals of 3D series. Table 1.13 Thermochemical data, KJMO1, for the first row transition elements and the standard electrode potentials for The. Reduction of M2 to M. Dot. Oxidation states. The transition elements usually exist in several different oxidation states which change in units of 1, e.g. Fe3 and Fe2, Cu2 and Cu. The oxidation states shown by the transition elements may be related to their electronic structures which have been already discussed in section 1.2 of this unit. Recalling the electronic configuration of the transition elements, we remember that Cr and Cu have additional stability when the d orbitals are exactly half filled or completely filled, table 1.14, in their icons. Table 1.14, Oxidation states of transition elements, the solid dots show common oxidation states, and the hollow dots show possible but unlikely states. Table 1.15, Oxidation states of transition elements of D block, the most common oxidation states are in bold type. If you look at table 1.14, then you will notice that there is a reduced tendency of higher states towards the end of the series. This could be due to steady increase in the effective nuclear charge along the series, thus pulling the d orbitals into the electron core and not making them readily available for bonding. For example, the only oxidation state for zinc is zinc 2, where no d orbital is involved. On the other hand, early in the series, it is difficult to form species that do not utilize the d electrons, i.e., Sc2 is virtually unknown in T5 is more stable than T2. By looking at table 1.15, you can very easily follow the trend in the oxidation states as we go down the group. The trend in the stability of oxidation states within the groups is different for the transition elements and the main group elements, S and P block elements. For the main group elements, the higher oxidation state becomes less stable going down a group because of inert effect. However, for the transition elements, the stability of the higher oxidation states increase going down a group. To illustrate this trend, let us first look at group 6. It is composed of Cr, Mo, and W. We have seen that chromium in 6 oxidation state as in potassium chromate is a good oxidizing agent, forming Cr3 as the product. This means that in many instances Cr3 is more stable than Cr6. In contrast, molybdenum and tungsten in 6 oxidation state in potassium orthomolybdate and K2WO4 are not easily reduced. This implies that lower oxidation states, e.g., Mo3 and W3, are not as easy to form as Cr3, making the 6 oxidation state more stable. Thus, the stability of the 6th state for group 6 elements will be W6 greater than Mo6 greater than Cr6. We find the same trend in group 4, which is composed of T, Zr and HF. For all the 3 elements, most stable oxidation state is 4. However, T2 and T3 can be formed from T4 by the use of good reducing agent, but lower oxidation states of Zr and HF are extremely difficult to prepare. Table 1.16 shows how various oxidation states of some elements of period 4 tend to react with respect to oxidation and reduction. Going from left to right across period 4, M2, UC, icons are known for the last 7 elements from V to Cu in M3, UC, icons are known for the first 7 elements from SC and company. Thus, there is an overall increase in stability of M2, UC, with respect to oxidation as one moves across the series. However, in the case of iron, Fe2, UC, is less stable than Fe3, UC, because of the extra stability associated with half-filled D5 orbitals in the case of Fe3, UC. SC could have an oxidation state of 2 if both S electrons are used for bonding, and 3 when 2 S and 1 D electrons are involved. T has an oxidation state 2 when both s electrons are used for bonding. 3. When 2 s and 1 d electrons are used, and 4. When 2 s and 2 d electrons are used. Similarly, V shows oxidation states of 2, 3, 4, and 5. In the case of crossing, by using the single s electron for bonding, we get an oxidation state of 1. Hence by using varying numbers of d electrons, oxidation states of 2, 3, 4, 5, and 6 are possible. Mn has oxidation states 2, 3, 4, 5, 6, and 7. In case of the first transition series, the lowest oxidation state displayed is the number of s electrons, and the highest oxidation state is the number of s and d electrons. The highest oxidation states are often stabilized in the oxide and fluoride compounds, e.g., MnO, Cro, Vo, Vf25, 2, 4, 4, etc. In these compounds, O2 and F are difficult to be oxidized by the central metal because O and F are strong oxidizing agents. Table 1.16 Reactivity of some oxidation states of first transition series. Elements in aqueous solution. Once the D5 configuration is exceeded, i.e., in the last 5 elements, the tendency for all the d electrons to participate in bonding decreases. Thus, Fe has a maximum oxidation state of 6. However, the second and third elements in this group attain a maximum oxidation state of 8 in RuO4 and Ozone-4. Can you guess why this difference between Fe and the other two elements Ru and Os? Well, the reason is the increased size of the atoms. The oxidation states form a regular pyramid, as shown in Table 1. 14. The oxidation number of all elements in the elemental state is 0. In addition, several of the elements have zero-valent and other low-valent states in complexes. Low oxidation states occur particularly with bonding ligands such as carbon monoxide and dipyridal. The higher oxidation states are displayed with electronegative elements like oxygen and fluorine. Compounds in higher oxidation states are oxidizing in nature and covalent, while those in lower oxidation states are reducing and ionic. Similar but not identical pyramids of oxidation states are found in the second and third rows of transition elements. 1.3 Stability of various oxidation states for Mn, Fe and Cu. Latimer diagrams. Latimer diagrams, also called reduction potential diagrams, show the different species of an element in varying oxidation states and are widely used to ascertain relative stabilities of different oxidation states. Arrows are put between different species and standard potentials involving two immediate species are written over the arrows. The oxidation state of the element concerned is specified under each species, which may differ by one or more electrons. The species with the highest oxidation state is placed at the extreme left and the one with the lowest at the right extreme. The first point to understand here is how to construct the Latimer diagram. You have to remember that in a Latimer diagram, oxidation members decrease from left to right. Then the numerical values of the standard potentials, E0, in volts are written above the line joining the species involved in the particular couple. Typically, standard conditions are taken in either strong acid, H equals 1 m, pH 0, or strong base, OH equals 1 m, pH 14. Latimer diagram for manganese, in 1 m acidic solution at 25 degrees Celsius, in oxidation states from 7 to 0 is shown below. If we now subtract the left-hand side, half reaction, from the right-hand side, half reaction, of the Latimer diagram, we get the disproportionation reaction, whose standard potential is given by dot E0 equals Yx, when Yx is positive, i.e. when the potential to the right of the redox species of the Latimer diagram is higher than that to the left, we have E0 greater than 0. This means delta G0, 0, and so the reaction is spontaneous, i.e. the species will disproportionate. 1.4 Summary. In this unit you have studied that periodic trends of properties like atomic radii, ionization energy, electronegativity, electrode potential and oxidation states of main group elements related to the electronic configuration of the atoms of elements. These vary in a more or less regular way, that is to say exhibit periodicity as we go across a period of the periodic table. Therefore, these atomic properties are also called periodic properties. Thank you for watching. We will see you in the next video with the next chapter.